Space Concordia Robotics Division is a multidisciplinary group of undergraduate and graduate students from Concordia University in Montreal, Canada. We are pleased and excited to introduce the latest iteration of our rover. The 3-bogie suspension from last year was enhanced to improve stability. This was done by replacing the single shaft used to link each bogie to the chassis. The new frame improves flexibility in mounting and removing modules such as the electronics bay, the science payload, and the arm. Closed-loop control for all DC motors in the arm guarantees accurate arm positioning. A new arm base assembly was designed to improve maintenance and reduce gear backlash. A custom-made slip ring was added to the arm space, both allowing an integrated solution to the cable management and increasing the range of motion. A new compliant adaptive gripper design was developed that interfaces with the arm's current and effector interface. The majority of the gripper is printed out using onyx material with carbon fiber particles and Kevlar strands. The rest, including the custom worm gear drives, were machined in-house. Its compliant fingers allow it to adapt to the shape of the object it is grasping. With the flexibility to type on a keyboard, grasp and insert a USB drive, or carry a 5-kilogram load, this design includes smart servos capable of position and velocity control. The battery consists of 56 lithium-ion battery cells providing power to all onboard components. An off-the-shelf, automotive-grade battery management system was added to better adhere to performance and reliance requirements. The new power distribution system controls and monitors the current flow to all motors in both the arm and the wheels using electronic load switches. Redesigns in the manipulator allowed the size of the electronics bay to more than double. An emergency kill switch located on the side panel of the electronics bay allows to mechanically break the current return path to the entire system. Remote communication with the rover's onboard computer is done by means of a digital radio module with MIMO functionality on the 900 MHz band. The base station uses a high-performance dual-polarity Yagi antenna. The rover has 2 perpendicularly positioned Omni antennas to capture both the horizontal and the vertical components of the dual-polarized radio signal. The command sequence begins at the base station, where signals are sent to the rover's onboard computer over the radio. The onboard computer then relays messages to and from the microcontrollers that control the wheels, arm, power distribution system, and science subsystems. 3 microcontrollers connect to the onboard computer through a USB hub. The 4th one communicates over UART. Last year's web-based user interface has been improved with the addition of new features, focusing on a design oriented for multiple operators. This includes revamping the existing components in such a way as to increase the efficiency of the flow of operations. Video feeds from cameras located around the rover give the operator a full view of the rover's environment. The rover can be controlled in one of 2 ways, through the graphical user interface or with a PlayStation 4 controller. The onboard computer was replaced for the NVIDIA Jetson TX2. This solves the bottleneck encountered last year. The additional computing allows for the computer to process large amounts of data during autonomous navigation. Our LiDAR allows for mapping of up to 120 meters of terrain. An AR tag detection ROS package uses camera streams to signal the rover when it has reached a post or a gate. Custom ROS scripts are being developed to then drive the rover up to the goal and flash the LED indicator. Together, they provide the rover's heading and position for autonomous navigation. The rover's scientific instrumentation comprises an off-the-shelf NIR spectrometer and a custom-made Raman spectrometer. The Texas Instruments NIR spectrometer is a reflectance spectrometer and is capable of analyzing the rocks for water contents. The Raman spectrometer was designed to analyze the soil for biomarkers which would indicate past and present life, as well as markers which would indicate habitability for present and future organisms.